Welcome everybody. Welcome to session two. This is the session where we're going to take a deep dive into Starknet and we'll learn more about it. In this session, the topics that we'll cover is Architecture 101. We're going to look at transactions, the different type of transactions, and the finalities on layer one and layer two. We're going to look into what are full nodes. And then finally, I believe some of you are really interested in the recursive proving. So we'll look at that as well. Last session, what we learned so far is that Cairo enables verifiable computation, and also the syntax is similar to Rust. We've seen like a small snippet of code, and we've seen this, how it looks like, and some of the struct, and so on. But what's new now is that initially what you need to know is that Cairo doesn't compile directly to this Cairo assembly bytecode. First, it compiles down to an intermediate representation that it's called Sierra, and then Sierra stands for Safe Intermediate Representation. After that, the Sierra file or program, or let's say file, gets compiled down to Safe Chasm, which is the Cairo assembly code. And the role of this, like why we need Sierra, is that before everything, so before Sierra, we initially were compiling Cairo smart contracts down to Chasm code. And in this situation, we had an issue. Failed transactions weren't included in the block. And this kind of like opened a DOS attack on the sequencer because the sequencer wasn't compensated for these rejected transactions. But now with the introduction of Sierra, like this intermediate representation, even failed transaction can be gracefully handled. And these failed transactions can be included in the block. And this means that the sequencer will always be compensated. And then there's no more denial of service vector as in Cairo 0. So maybe for those who are not familiar with the Cairo 0, it's basically like the initial language that was created by Starknet. And it's a very low-end programming language that looks something like Python, I think. But we're past that. So no more Cairo 0, it's only Cairo from now. Okay, and one last thing is that another benefit of decoupling these components is that it means that we now can independently or change these components because we have this abstraction layer called Sierra in the middle, right? And we can update these components independently, right? The Safe Chasm and the Cairo smart contracts. Are these compilation steps only for Cairo smart contracts? Yeah. I think it's in general for Cairo, because if you want to generate a validity proof with it, you have to compile down to Sierra. So in essence, it stands for all Cairo codes. So in this case, we have
I'm just guessing that the Safe Chasm would be necessary for just regular Cairo. Yes. The Safe Chasm is just for revert.
Exactly. Yeah. So basically, with Safe Chasm, like it helps with the revert transactions. And one thing that I maybe forgot to say is that the sequencer compiles the Sierra file to Safe Chasm. It's not the user that does that. So it's the sequencer that does that. So initially, we had this story in the first session where we have, like our space exploration team trying to build or to answer some questions, and they built a program in Cairo. And this program in Cairo was sent to a rival country that had a supercomputer, because the country that the space exploration team is in, they don't have the resources or capabilities to run this complicated program. So the program is being sent to the rival country, they execute it on your behalf, and they will send the result and the validity proof attached to it. Right. So now from this example, we want to understand the internal modules of Starknet. And we'll take this simple example and we'll construct upon it. But just keep in mind, this is a very simplified version of the internal modules. So in this case, we have your laptop in your country. You have the Cairo program. You compile down to this intermediate representation, safe intermediate representation called Sierra. And you send this file to the supercomputer of the rival country. The supercomputer receives this file. It compiles down to Chasm, the Cairo assembly bytecode, and then it will run it in the Cairo virtual machine. After that, there's another module called the prover, where the trace of this execution is being sent to, and then the validity proof is being generated. After the validity proof is being generated, it's being sent back to the verifier, to your laptop in this case, and additionally, the result is being sent back. Now, let's look at the Starknet modules. So we have the same example, but now we start building upon it. We have the laptop, we have the Cairo program, we compile it down to the Sierra file, and then we send the Sierra file to the sequencer. So the sequencer is like a big machine that does a lot of things. So the sequencer is quite a complex machine. And we send this file to the sequencer on Starknet. It compiles the file to Chasm, and then basically it runs on the Cairo VM. And what happens is that it generates it creates the trace of these execution, and it will send it to the prover, the another module, which here it's called Sharp. So it's called Sharp because it's an abbreviation from shared prover. And this shared prover is basically shared with other protocols, with Starknet and Starknet and other, but we'll get to that in a second. Now, Sharp or the prover will generate the validity proof, and then it will send it to the verifier on Ethereum, which the verifier basically is another Solidity smart contract. And this is where, like the Ethereum node operators are picking it and verifying it. And then you also get back the result out of that. Why don't we compile it to Chasm before sending to the rival country? Right. So that's a good question. So basically, to be able to gracefully handle this failed transaction, the block, the sequencer has to compile this file to what we call safe Chasm. And this basically will give us certainty that these failed transactions can be handled gracefully. Because if you compile it down directly to Chasm, we are not sure that you'll be able to gracefully handle this. Okay, so as I mentioned, this is an oversimplification of how the Starknet module looks like. Another question is, why oversimplify? Well, Starknet uses smart contracts. If you want to interact with Starknet, you're going to interact with a smart contract and not plain Cairo code. And before executing a smart contract, you have to perform two steps. The first step is declaring your smart contract. This is a unique feature to Starknet compared to Ethereum. And then the second one is deploying the transaction. So kind of like, you can think of it like declaring a smart contract as registering a blueprint, and then deploying the smart contract as creating an instance of that blueprint, like of the registered blueprint. And now users can interact with Starknet via transactions. So whenever you try to interact with a smart contract, you submit you create a transaction, and that's how you interact with Starknet. And finally, one thing that's very important is that all transactions must be signed. So let's analyze how this process is in detail. How do you declare a smart contract? So again, we have the same example that we used before. We have the laptop. We have your Cairo smart contract, and then this smart contract gets compiled down to Sierra. Then you have a wallet where basically you are able to create these transactions. So this wallet could be Argent or Bravos. It could be your laptop. It could be your smartphone. It could be anything, right? And then this wallet allows you to create these transactions. And in this case, we're going to create a declare transaction. So what happens is that we create that declare transaction, and we send the Sierra code with that. And it arrives to the sequencer in something that we call mempool. And it's a place where transactions are waiting in a place like where they get collected. Then the sequencer picks up this transaction from the mempool. It compiles it down to Chasm, and then this the question is like, what do we exactly send to the prover? Can we can we actually send the proof of the compilation of the smart contract, or that's not really the case? Well, in order to do that, the compiler has to be written in Cairo, and currently the compiler is written in Rust. So it's not really possible at this point. But now the question may arise like, okay, how do we know that the sequencer here is actually not cheating, and it's using the same Sierra code, and it's not cheating after all? And this is where we come to proving compilation. So Because the Cairo compiler is written in Rust, we cannot actually prove the compilation of the smart contract. A long-term solution would be is to write this Cairo compiler in Cairo, and then compilation can be proven. However, like a stopgap solution, like temporary solutions, is what we can do is we can provide the chasm hash while we declare the this declared transaction. Then we let the sequencer recompile the Sierra file to chasm, and then the sequencer can compare these hashes, and then it can be sure that we can be sure that the whole process has been made correctly and the sequencer hasn't cheated. So let's see how this actually works. So we have the same setup before. We have the laptop, we have your Cairo smart contract, we compile it down to Sierra, and then we compile it down to chasm. With your wallet, we'll be able to create a transaction. That transaction is a declared transaction. And now, additionally to the Sierra code, you also send the chasm hash. It arrives in the mempool, in the place where the sequencer receives all the transactions. And once it picks it up, it will compile it, and then it will compare the chasm hashes if they match together. And this is how we actually able to solve this as a stopgap solution. As I mentioned, in the future, when the compiler will be written in Cairo, this won't be necessary anymore. Let me see if there are any questions so far. No, we're good to go. Okay, now let's discuss about declaring versus deploying. Initially, when you declare a smart contract, you register the code on Starknet. This declaration of the smart contract is also known as a contract class. And this is identified by unique class hash, right? These contract classes, you have to understand that there's only pure code to it. They don't have any storage attributed. So it's just, it could act as a simple blueprint that's registered to Starknet. No storage, only a unique class hash and the pure code itself. Now, when you want to actually create an instance of this contract, you can derive it from a contract class. So this is like the similar type of like OOP in programming, right? You have your blueprint, and then you can create instances out of that blueprint. Initially, what you have to do is basically whenever you want to declare or like create an instance, you have to pass the class hash of the contract class, and then you have to pass constructor call, like the constructor function, the call data that the construction function accepts. And then you can create these instances, right? So you can see how powerful this method is. One example, maybe it's worth to say, is that you have like an ERC20 token or maybe an ERC721 from OpenZeppelin. You declare this as a blueprint, as a contract class, and then you can derive multiple instances from that contract class. And one important aspect here is that each of these instances has their own unique storage, right? And it's identified by a unique address. So just to recap, contract class acts as a blueprint that has a unique class hash. It's pure code. They don't have anything else besides pure code. It's no storage, nothing. And then deploying contracts is basically creating instances of this contract class. And then these contract instances have unique storage attributed to it, a unique address. Make sense? What's the benefit for declaring contract before deploying? So I'll get to that in a second, but this is how like the whole module works on Starknet. We'll cover that in the next slides, like the reason why we have to declare transactions and then deploying. Okay. This is where you come to the universal deployer, right? So initially, because like universal deployer is like what you have to understand is that it's a smart contract that deploys other smart contracts, right? And this is part of the account abstraction, which I think it's similar to the ERC 4337 on Ethereum. They also have like a universal deployer. And all of this is basically happening under the hood, right? The universal deployer only has one selector that you're using. It's the deploy contract function. And then this selector has to be invoked with the blueprints class hash and the constructor arguments. So let me recap. universal deployer, it's a simple like smart contract that allows you to deploy other smart contracts. And this is because how like the count abstraction is being built on Starknet. You'll have to pass the blueprint's class hash and the constructor argument. And I think after this slide, I'm going to show you the UDC as an example. But what you have to understand is that internally, it uses a syscall called deploy. And this is basically a public good that's created by Open Zeppelin. The universal deployer smart contract is currently, the one in production is currently written in Cairo 0. But I believe there's also a Cairo version that's currently not in production. But actually, let me show this to you. So we have the UDC here. I already prepared them in advance. Let's see, what do we have here? So this is the universal deployer. How you can access it is that you can go to like Starknet in this case, and then you can go to, I think it's developer address book. And then here down below, you're gonna see Open Zeppelin universal deployer. And this is the public good that everybody uses to deploy smart contracts, right? So you can see like these are the events, and this is basically like the universal deployer. The class version is Cairo 0, and I believe you can even check the code itself. So this is like the universal deployer, and you can see that it's a Cairo 0 code, and then this is the deploy contract that everybody uses, the method that everybody uses. And then inside here, you have the class hash, and then you have the call data, or basically the constructor function argument. So let me see. So there's a question. Since the universal deployer is the smart contract that deploys other smart contracts, how can the owner of the deployed smart contract be setting using MS sender? Because at that point of deployment, the universal deployer will be using MS. So basically, we don't have MSG sender. That's something that comes from Solidity, right? Whenever you deploy a contract, right, I have already a wallet. And then that wallet will send the class hash, and then it's going to send like all the call data. And basically, you'll be able to get like here, like get caller address, you see? So this is, you'll be able to get the address of who is calling it, the deployer actually. Okay, now just to show the other universal deployer contract. So this is the Cairo version, the new version. And then you can go to the docs Open Zeppelin, and then you can check out the contract, the UDC contract. And I think they also have it available on the GitHub repo. So you have it here, the universal deployer, Open Zeppelin Cairo contracts, and then you have the new version as well. But this is currently not in production. So the one in production that we have is the Cairo 0 version. Okay, one last thing that I want to show, it's mainly going back here. So the declaring versus deploying. You might remember that from last session, David did an example of actually, like creating a wallet and then declaring this, I think deploying this wallet on mainnet, right? So what we can actually analyze is that how these, like I have a simple wallet here. I'm gonna grab the address of the wallet. I'm gonna add it to the Starknet. And now I want to show you like the differences between the blueprint that we're using, and then, like this is basically coming from a blueprint. So the class hash that we used, or the contract class that we use, is this one. This is the registered blueprint on Starknet. This is just pure code with no storage. And you can see how many deploy contracts there are from this. So there's, I think, over almost 600,000 contracts that are being deployed from this contract class, right? And then I have my own, account contract that has its own storage, its unique address, and so on. So this is how you can actually verify this. Okay, now let's get back to our presentation. So now let's take a look at smart contracts, classes versus instances. So initially we use the declare transaction to declare a smart contract on Starknet. And we use an invoke transaction to actually deploy or create an instance of this contract class. We use an invoke because we basically change the state of the network. And with this invoke transaction, we're going to call the deploy function from the universal deployer. Whenever we call this deploy function, we pass the constructor arguments for that contract class. So the constructor arguments, so for those who are familiar with Solidity, you always have like a constructor function in your smart contract that has some initial settings that are being made once the contract is being deployed. And that's the first function that runs. Those are the constructor arguments. And from here, a smart contract instance is being created. But there's also another way to use contract classes. And that other way, it can be used as a library. So what this means is that we do the same thing. We declare the transaction. We create a transaction of declared type. We have the smart contract declared on Starknet. And now what I can do is basically I can use my smart contract to create an invoke to this contract class. So I'll do like a library call. So you can imagine that I'm only using this contract class as a pure code. And then this could, like help me run a certain computation or something like this, right? So it acts as a library call. These are like two ways that you can think of contract classes. So David, could there exist any other deployers beyond UDC, or is it a special contract? So yeah, so good question. So UDC is just a special contract for Starknet that incorporates the account abstraction. And this is the way that we deploy contracts on Starknet. So UDC is a special smart contract that allows us to deploy these contracts. Deploying a smart contract. Now, let's analyze this in more detail. So we have your laptop, we have the wallet. And what happens is that you initiate an invoke transaction. So remember, in the first time when we declared the contract, we had the declared transaction. But now we have an invoke transaction. And in this invoke transaction, we're going to add the universal deploy address, the one that I showed you on StarkScan, so that address. You're going to pass the class hash that you want to create an instance from. So if I want to create a Browse account, then I'm going to pass the class hash of that Browse account. And I'm going to pass the constructor arguments that are expected in the function. This invoke transaction arrives in the mempool in the sequencer. The sequencer picks up this transaction. They're going to it's going to execute the transaction, the KRVM. The constructor function is also being executed. And then the trace is being sent to the prover, to Sharp. And from here, the validity proof is being generated by Sharp. It's being sent to Ethereum, to the verifier. Again, a reminder, the verifier is just a simple Solidity smart contract. And you can also check that out if you want to. But as a return, you also get back the address of the deployed instance. So that's what you get back, like the address of the deployed instance. Now, yeah, so just to recap, we have like invoking a smart contract. What's a little bit different, here it's basically deploying a smart contract. So this is how we deploy the smart contract with the universal deployer. But now when we want to invoke like a normal function of a smart contract, it could be like a simple transfer or whatever you can think of. What we have to do, what we have to pass in this invoke transaction is we pass the smart contract address, right? We pass the function selector. So maybe like this one will be the transfer function selector. And then we're going to pass the arguments for that particular function that we need to give. What happens is the same process. It goes to the mempool. Then from the mempool, it's being picked up by the sequencer. It's being executed in the KRVM. The function is being executed there. Because remember, even smart contracts, they have like Cairo code attributed to it. So we have to execute those functions. The trace is being sent to the prover, to Sharp. The validity proof is being created. That's sent to Ethereum. And then the result is being sent back to you. So maybe this is a good opportunity to also showcase this. So this is the verifier on layer 1. So this is the contract that verifies the validity proofs on layer 1, and you can analyze this in detail if you want to. So use the contract, and then you have here all the things associated with it. Okay, now to summarize Architecture 101, it's important to know that Cairo compiles to Sierra and not to the Cairo VM bytecode. So the first step that happens is it compiles down to Sierra, and then the sequencer will compile the Sierra to SafeCasm. And Another important thing is like, why is this? Is because we want to include failed or even rejected transaction in the block. And Sierra is able to gracefully handle this. Declaring creates a contract class, and then contract classes or contract instances can be derived from the contract class. So the contract class is a blueprint, and then whenever you want to create a new instance, you can create it from that blueprint. A contract class can also be used as library. So you can use that pure code declared on Starknet, and then you can use it to execute a certain function. I don't know, something that's helpful for you. Chasm hash is used to prove the compilation. So you'll remember where we want to, know that how the sequencer is not cheating is because we send the chasm hash and we compare this to the sequencer, the chasm hash, and if those two are matching, we can be sure that the sequencer is not cheating. And deploying requires the universal deployer, right? So this is part of the account abstraction model that we have on Starknet. And finally, there are two important transaction types, declare and invoke. Good. Now, on to the next topic, transaction. So as you remember, like this is where we left off. We have the smartphone, your wallet. And with your wallet, you can initiate a transaction. And then this transaction, it basically arrives to the mempool, to the sequencer. In the mempool, there's some certain transaction validation happening. And if the transaction validation is correct, then the transaction is picked up by the sequencer and is being executed in the care VM. Then the trace is being sent to the prover, to the sharp. Again, sharp is the shared prover that's being shared for multiple protocols, not only Starknet, but with Starkx, like DYDX, Sorare, Rhinify, and so on, Herodotus, and so on. And then this, the prover generates the validity proof that's being sent to Ethereum layer 1, the verifier, which is another smart contract written in Solidity. And finally, the result is being sent to you. So this is just kind of like a recap of where we left off. Now, let's analyze how like a transaction lifecycle into the whole Starknet module, right? So it all starts with your smartphone, where you initiate the transaction and you sign this transaction. And then in the mempool, basically, we're doing some transaction validation. And here we check if the transaction has the correct structure, and basically like we check if it has correct structure. And based on this, it could be the transaction can change to received, or it will be ignored. But please keep in mind that ignore is not actually a transaction state. It will just be simply ignored by the sequencer, right? So if the correct structure, if the correct structure is valid for your transaction, then it will change the status of receive. So the sequencer is aware of your transaction, but that's about it. Like it's aware that it exists in this mempool. Now, what happens next is that we have signature validation, and this is this is an important step to actually check that the signed transaction is actually made by you. So this is where we check if the signature is valid. In case the signature is invalid, the transaction will be rejected, and that's the end of it, right? However, if the transaction is valid, the status will be unchanged, and it will continue in the path. So what happens next is that it arrives to the KOVM, where basically your transaction is being executed. And here it could have two different transaction status. If everything went well, like if the transaction has processed correctly and it's valid, then it will receive the transaction status of accepted on layer 2. In case there was some issue, like maybe you didn't have enough gas associated with that transaction, or maybe there's an assertion failure, like you've checked for 1 = 1 and it wasn't, right? Then the transaction status will be reverted. And this is the reverted transaction that will be included in the block that we talked about. We are able to gracefully handle these type of transactions. The trace is being sent to the prover, to Sharp. And once Sharp creates the validity proof and the verifier on Ethereum validates, like confirms that the validity proof is correct, which means that all of the node operators, the thousands and thousands of node operators verify this validity proof, then the transaction status will be changed to accepted on layer 1. So accepted on layer 2 is the finality on layer 2, and then accepted on layer 1 is the finality on layer 1. Okay. Let me see. Validity proofs are generated for reverted transaction also. Yes. So that's the one thing that Sierra helps with. It allows us to gracefully handle this type of transactions, and these transactions are included in the block and basically will become part of the validity proof as well. And with this, even sequencers are being paid for the amount of work that's being done for executing this transaction. Okay, accepted means how many confirmation, or is it final? So accepted on layer 1 is that it reaches like it's a final. It's in like finality. You cannot modify the state of it. That's what it means. How many number of confirmation? Well, that's a good question. I don't know how many confirmations does Ethereum need to validate a block? Not entirely sure, but yeah. So finality means that you're unable to change the state of it. That's when the finality happens. Okay, now I'll move forward a little bit. Now, here I just want to go through like the different transaction types that we have on Starknet. And the first one we already talked about is the declared transaction, which basically allows you to register new code to Starknet. Then we have the invoke transaction, which basically allows you to execute write functions. And I guess you'll learn about this. Like these write functions are basically able to modify the state of the network, and because you're modifying the state, you have to pay a certain amount of fee. But now there's another special type of transaction, and this is called the deploy account. And what this does is basically it deploys an account contract. And this is important for smart wallets. So we talked about smart wallets in the last session, but now we'll explore like how this deploy account works and why do we need it. Again, all transactions that modify the global state, you have to pay gas fees because you change the global state and you have to pay for the fee for that. And then if you just, read a certain, like you have a read-only function that mainly returns like who's the owner of this account and returns like the owner. It's basically just a read-only. You don't modify the state of the, or you don't modify the global state, and there's no gas associated with it. But now there's a question, like, isn't there like a deploy transaction? And well, the case is that not really. We don't need a deploy transaction, and that's because we have the UDC, the Universal Deployer Contract. And the Universal Deployer Contract, if you remember, that's the thing, the public good that we use to deploy these contracts. And to deploy or to interact with the UDC, you actually create an invoke transaction. So we use the same invoke transaction to deploy contracts. Does that make sense? Accepted means how many? Oh, okay. Okay. Now on to the next dilemma, right? So this is a sort of a dilemma that we're getting into, and this is where we're gonna talk about like the deploying an account contract. So we previously mentioned briefly that in the last slide that this transaction type is a little bit special. It's because it allows you to deploy. So let me rephrase it. So this deploy account, like this deploy transaction type, is a little bit different from deploying normal smart accounts. So if you look here, we have this deploy account, and then this basically what it means is that if you want to create a smart wallet, right, you'll have to deploy an account contract, and if you want to deploy an account contract, you have to pay gas fees for it. But to pay gas fees for it, you have to have a smart wallet. So this is where we get into like this sort of a dilemma, or like the chicken and the egg problem, or like the circular reference, right? To deploy a smart wallet, you actually need a smart wallet, which is not technically ideal because you should be able to deploy an account contract without having a smart wallet. So if you remember from the last slide, from the last presentation, with the account abstraction model, is we decouple these two together from it. Like we have the signer and the account contract independently, right? So now the question is like, how can we do this? How can we solve this? And there's actually a solution for this. So the solution is actually counterfactual deployment, which basically stands like a counterfactual contract is a contract that we can interact with even before we actually deploying it on chain. And this is because on Starknet, deployments are deterministic, and it allows us to predict the address where the contract will be deployed. And this allows us to leverage this property. And the property is basically we'll be able to make the contract pay for its own deployment by sending funds in advance. So we pre-fund this. So what happens here is that we calculate the address off-chain. Like this is done by wallets automatically, like for example, Argent and Bravos. And also just to notice that this happens under the hood. Like as a user, you don't have to worry about this. It's just mainly stating what's happening behind the scenes. So Bravos and Argent, they calculate this address off-chain because we already know exactly the class hash that you're sending, that you're using, and the constructor arguments. We pre-fund this wallet, and then we're going to make the account contract to deploy for its own deployment by using the deploy account transaction. And then the sequencer will automatically deduct the gas fees from that address. So again, this happens under the hood. You don't have to worry about it. And if you have used like the wallet, like I don't know, like Argent or Bravos, and you made a transfer on, let's say, Avenue, it automatically, you don't even have to worry about like deploying the contract because like wallets like Argent and Bravos will automatically include this into a multi-call. And first they will deploy the account and then they will do the transfer. I think the last slide, last presentation, David showed like how you can manually deploy a wallet. But basically, like if you do a transaction on Avenue, this will automatically deploy your account contract. You don't have to worry about it. The only thing that you need to do is like send the funds. So maybe I don't want to go into the details of the like showing an example. It will take a bit of a time, but basically whenever you add a new account, let's say add a new account here, you see like I already have my address, it's pre-calculated off chain. And then here, what I can do is basically go back to my different account. I can pre-fund it, and then I can either do a transaction on Avenue, and it will automatically deploy my account contract in a multi-call, or I can manually go to, I think it's just like here, and then once I have like some pre-funded, I can manually deploy it on chain. So this is automatically done by the wallets. Okay, now just to kind of like do a summary of the transactions. The three type of transactions that we have is declare, which basically register this blueprint. Invoke allows you to interact with the UDC to deploy or create instances from these blueprints, or even interact with smart contracts to do like transfers or anything else. And then the deploy account transaction type that's used to deploy account contracts for wallets. The transaction lifecycle is like this. First, received, it arrives in mempool. The sequencer is aware of that transaction, but hasn't done anything with it. Then the next one is accepted on layer 2. This is the finality that we have on layer 2. Then there's accepted on layer 1. This is the finality of layer 1 once the validity proof is sent to the verifier on Ethereum, and the thousands and thousands of nodes verify this. And finally, there's rejected and reverted transactions. For account contracts, there's a counterfactual way to do this, the counterfactual deployment that allows us to pre-calculate the account contract address in advance and pre-fund this account contract to support its own deployment. So there's a question: can finality get accepted on layer 2 and get rejected on layer 1? Can finality? Yes. So usually like that's rarely happens. So when like the layer 1 validity proof is being rejected, usually happens very rarely in like case of upgrades, like massive upgrades. And what happens at that point, I believe there's a reorg happening, but it's very rare, like such cases. As a rollup, does Starknet have a state? If yes, I will be more volatile than ETH. It's that a lot of computing if reverted now to Starknet have a state. So we will explore during this during full nodes. So I think your question refers to the full nodes, and we'll take a look at that in just a second. Okay. So this is the transaction finality that we'll discuss here. So initially, if you remember this slide, we had it in the first session where we discussed the L1 finality, where Ethereum usually takes about 6 minutes to reach finality, while optimistic rollups can take roughly about 1 week to reach finality. And this is because how optimistic rollups work in general. So that means that if you want to transfer something from optimistic rollups to L1, it roughly takes you 1 week to actually be able to use those funds, for example. But on Starknet, the finality is roughly about 10 hours. And this is not to be confused with the layer 2 finality. And now you'll see that there's 10 seconds there, which is crossed over. And the reason why, and you'll see, I think the crossover you'll see initially for the first time, and after that, you're going to see only the 2 seconds. And the reason why I did this is because we were at an important process or an important part where there's an important upgrade that's happening, and it's called V013.2. And this upgrade addresses this layer 2 finality and block creation and so on, right? So it's a massive upgrade that will improve tremendously, like the TPS and the layer 2 finalities. And in the previous version, it was 10 seconds, but now with the new upgrade, it's 2 seconds. This upgrade is already available on Sepolia, but it will take place in mainnet by the end of the month, I believe. Okay, so let's analyze layer 1 versus layer 2 finality. So if you remember, we have the same diagram as before. Where are these happening exactly? So we have the wallet. You send a signed transaction to the mempool. The sequencer picks it up from the mempool. It executes in the KRVM. The trace is being sent to the prover. And then mainly here, what's probably something new is that we have this DA data and the blob, right? So what happens here is that the prover sends the validity proof to the verifier, and then the DA data is basically the current state of the network that's sent to the blob data. And this is kind of like, I think it's an unstructured data, and blobs are specifically for rollups in general, or for layer 2. And then this is only with the Denkun upgrade that happened with EIP 4844. And what happens on Ethereum is basically you're able to do 2 types of transaction, like the normal transaction that you have, and then the transaction data. And then this enabled layer 2s to massively become much more cheaper, because this type of data lives for, I'm not entirely sure for how much. Is it 1 month or 18 days or something like that? But basically lives temporarily, and it's used for that amount of time. Okay, now where are like the L1s and L2s finality happening? The layer 2 finality happens when your transaction has been executed or successfully executed in the KRVM. And this roughly takes you about 10 seconds, right? This is where you achieve the layer 2 finality. The layer 1 finality, you achieve only after the whole process finished. So you sign the transaction, goes to the KRVM, goes to the prover generates the validity proof, and then only when the thousands and thousands of nodes that verify this validity proof accept it and validate it, only then it reaches the layer 1 finality. And this may take roughly about 10 hours, right? And even like we can verify this like by hand. Like if you go to this contract, you can notice like the difference between the proofs that are being sent. So you can see like this one was 10 hours ago, this one's 1 hour ago, and then you can analyze individually. Okay. Now, let's take a look at these 2 in particular. So the layer 2 finality, as I mentioned, takes 2 seconds, and this is with the version 13.2 upgrade. And an important thing is that you have to trust Starkware, since no validity proof has been created yet. And you have to trust the sequencer that is doing its job, right? And you can see that the L2 finality happens here. So you have to trust the sequencer and Starkware that they're doing the right thing. And this is the finality that's being used by most of the applications on Starknet. Now, regarding layer 2 finality, it takes roughly about 10 hours, and we've seen the verifier contract and how these validity proofs are being submitted. It's completely trusted because at that point, the validity proof is verified by these thousands and thousands of node operators on Ethereum independently. And this is mostly the finality that is used by bridges to extract data. Okay, now we talked about this previously, the mempool, and there's it's not necessarily a notation issue, but I just want to clear a few things out. So initially, there's no fee market on Starknet yet, right? The transactions basically arrive in the same order they come to the mempool. So this is like the first in or first out. No, so first in, first out queue, or first come, first serve. There are two different notations, but they are same. So they're executed in the order they arrive, and you cannot actually pay more fee, like a higher fee, to actually jump the queue. That's not possible yet. So the Starknet mempool, you have the first in, first out queue, and there's some certain basic transaction validation to see if like the transaction has the correct structure. On Starknet, we usually refer to this term as a batcher, and the term basically mempool implies to be like kind of like a decentralized mempool and being shared with multiple nodes. But currently, because the sequencer is centralized, we call it as a batcher. A real mempool will be created for peer-to-peer network, and that's part of the decentralization roadmap that will come. Okay, now let's analyze the pending block. So this is the block status, like the pending that we have, right? We have created a fresh block, and now basically in this fresh block, the pending block, a new transaction arrives to the sequencer. This is being inserted in the block status, and it's being added to the pending block. And once it's being executed, the transaction status will be changed to accepted on layer 2. And this is the layer 2 finality we talked about, the 2 seconds, right? Now, let's take another transaction that arrives into the pending block. And then this new transaction arrives to the sequencer. It's being picked up from the mempool, and it's being the same process is being repeated. The transaction gets executed. The transaction status would be changed to accepted on layer 2, and this is the layer 2 finality. Now, once the whole block size reaches a certain amount, and this certain amount, you see that previously was 40 million. This is in the previous version, but with the 13.2, the new limit is 45 million carob steps. So when this max size is reached by these transactions, then we change the status of the block to created. That's when the block is being created. Or what's also important is that each transactions have certain amount of limits. So the maximum size of each transaction can be 10 million carob steps. And I'm not entirely sure how to put 10 million carob steps into the picture, but you can think of like Games Influence, which is kind of like a space exploration game. They can actually simulate realistic orbital mechanics and flight simulation, or you can do even ZKML. You can imagine it like that. Carob steps are basically computation steps that are measured as carob steps. That's basically it. And previously, a block was created every 3 or 6 minutes. But now with the new upgrade, this has been reduced to 30 seconds. So this means it's quite fast. We'll see, like if you actually checked like Sepolia, like we can actually quickly check that. I don't see any harms in it. I think it's Voyager, and then we can check Sepolia. We can see like this is like the new like the upgrade, like the 13.2, and the max ever recorded is 583, which is transactions per second, which is quite a lot. So I'm really looking forward to it. Okay, back to our pending block. So we've seen how a block is being created. So you have the pending status, the block is open, and it receives transactions. And once the maximum number of or maximum size is achieved for the block, then it's being created. Or I believe like when the 30 seconds have passed, it's going to be closed again. Okay, so now let's look at this as a timeline, an event timeline. And the distribution is not at scale, so take it with a grain of salt. So the sequencer receives it in 2 seconds, we achieve layer 2. A block is being created in 30 seconds, and then layer 1 finality is achieved every 10 hours or so. Now, to summarize this chapter, the transaction finality. Transactions are all executed in the order they arrive. First in, first serve. or FIFO, so first in, first served, or am I mistaken? Which come? So it's like first in, first served. That's basically the order they arrive. They execute in the order they arrive. Next, new transactions arrive into and they are added into a pending block. Transactions are executed right away. So basically, once they reach the KVM, the layer 2 finality is achieved, and this is the 2 seconds. The layer 2 finality happens before the block is even finalized. So as you know, a new block is created every 30 seconds, but you achieve transaction finality way faster. And then a block can hold up to 45 million chaos steps. And then finally, a transaction can hold up to 10 million chaos steps. So that's basically the summary of transaction types and transaction life cycles and how a new block is created for Starknet. So full nodes. What are full nodes? So to quickly answer this question, it's basically a full node answers questions about the Starknet state. It means that it is a node that knows the current state of Starknet, and you can query all the data on the Starknet blockchain. Users don't directly interact with the sequencer, only full nodes do. So this is mainly because an advantage to this is that we reduce the load of the sequencer. The full node is kind of like equivalent to an execution client on Ethereum. And you can use an RPC server to get the information about certain transactions. Starknet has currently 4 different full nodes for clients in this case. We have Juno from Nethermind, and this is written in Go. Then we have Pathfinder from EQ Labs, which is written in Rust. Then we have Papyrus from Starkware, which is also written in Rust. And finally, we have Madara, which is a community project that's written in Rust. And these full nodes expose the RPC servers, and you can find like the specifications on that link. Okay, now let's look at an example how we are reading from Starknet. So imagine you have your smart wallet or smartphone with your wallet, and you make a request to these RPC. And then this RPC can be like, you can use like services such as Alchemy, Infura, Blast, Voyager, or you name it. You even can have your node. And then these expose like an RPC that you communicate or you do the request from. And this will basically will read and it will look at the state manager of the Starknet, where we have the database and the KOVM as well. And what happens here, like if you find the request that you want to get, then this is being sent back as a response to the wallet. No need to interact with Starknet at all, since the full node has everything that you need. On a regular basis, the full node updates itself periodically. And what happens is that it goes to the sequencer, to the feeder gateway, and here basically it will fetch the latest state of the network, and it will update automatically the database with the latest block. This is how a full node can stay in sync with the current state of the Starknet. It's kind of like similar to Ethereum full node. Now, writing to Starknet, it's a little bit more complex than this. And buckle up, because I think this will be a very insightful chart. So we have your smart wallet, or smart. I keep calling it smart wallet. It's your smartphone with your smart wallet, right? You sign a transaction, because now writing to Starknet, it's basically an invoke transaction, right? So we changed the global state. So that's why we have a transaction, and this transaction is being signed. And basically being like an invoke transaction, the full node doesn't really it passes through the full node directly, right? So you don't actually read from the full node. You just want to make a change to the Starknet. So what happens is that you send this transaction to a full node, and then the full node will pass this transaction along to the sequencer, and it will arrive to a new module called the gateway. This is like a temporary solution to query the sequencer states like endpoints, and you have like the get block, the get class hash, and so on and so forth. But it arrives to the gateway. It arrives, then the signed transaction arrives in the mempool. And this is the where you kind of like already know the steps. It arrives in the mempool, and then here it's being sent, like the transaction arrives to the state manager with the database and the Caravia. And finally, what happens here is we introduce a new term here. It's called Starknet OS. But basically what happens is that, like the new block is being created, is being bundled together, and then the Starknet OS is just, you have to think about it as a Cairo program that takes the current state of the network, process the new transactions and blocks. That's what the Starknet OS does. And currently, if I'm not mistaken, it's a Cairo program written in Cairo 0. Then the execution trace is being sent to the sharp, the prover, and this is where the blockchain writer, which kind of like is in charge of the interface during the verification of the validity proof, sends it to the verifier on Ethereum, right? So this is the validity proof that's being sent from the blockchain writer. And then what we have is we also have the DA data that's being sent by this blockchain writer to the blob data. So there's a lot of things to take in, but this is kind of like how writing to Starknet works. Again, this happens under the hood. You don't really have to worry about this. Now, I think there was a question in the QA, and it was like, how do you know like the current state of the Starknet? And there's something called L2 block checkpoints, right? So once what we have to do is that once a loop is being created, like you have like the sequencer, you have these blocks that are being sent to the Starknet OS, it executes the transaction and creates a new block. The new trace is being sent to the prover, and the whole thing is being processed. There's basically like, once this loop is being done, there's a module that interacts with this checkpoint. And this module is called the Starknet operator. And what the Starknet operator does is basically it interacts with another Solidity smart contract. It's called SN core. And this performs a periodic checkpoints of the layer 2 state. And how it does, it basically interacts with this smart contract, with the transaction per block. And then in this transaction per block, they only send the key variables. So we have the block number, the block hash, and the global root hash. These are the main important things that are being sent as a transaction. And this is a way to do a checkpoint of the state of layer 2 on layer 1 as a simple transaction. So thinking a layer 2 full node. This is like the example of Pathfinder, how it works. So we have Pathfinder request a new like a new layer 2 block is being produced from the sequencer, so it's being requested. Then it calculates the root hash of this layer 2 block, a new block. And then what happens is that it compares the root hash of the layer 2 checkpoint on layer 1. So we take this calculated root hash and we check this layer 2 checkpoint on layer 1 that's being created by the SN operator here, right? So this is how like the syncing on a layer 2 full node works. So we calculate the root and we check this root hash with the layer 2 checkpoint on layer 1, right? That's done by the Starknet operator. And if these are matching, then we mark the layer 2 block as valid. And if it's not matching, then the layer 2 block is marked as invalid. This, I think, might change in the future because the plans for decentralization will come. And then I believe like this architecture will change a little bit. Okay, just to summarize the full nodes here quickly. So a full node answers questions about the Starknet network and the Starknet state. Basically allows you to query all the data of the Starknet blockchain. There's 4 implementations of full nodes. So we have Juno, Papyrus, Madara, and Pathfinder. Now this one, so the state manager, I think I forgot to mention this, but basically like the state manager is part of the sequencer. And I'll show you after this slide. But basically like what happens here, like where is it? Like the state manager, like as I mentioned here, is part of the sequencer, right? It's embedded in it. The sequencer is quite like a very complicated machine with a lot of modules. That's how you might want to refer to it. Okay, so the state manager is part of the sequencer. Starknet stores the block roots on Ethereum, and this is to do the syncing on layer 2 full nodes. And they can be used for block verification. And Starknet Core is also used for layer 1, layer 2 messages, but we won't get into that because that's a more complicated subject for that. So for the last part of this session, we're going to talk about recursion, especially recursive proofs, or recursive proving. Now, maybe you remember this slide from the last session, and we talked here about like the execution versus verification. And just to recap, what we have here is that here on the left side we have the sequencer, and X is basically the number of steps that is performed by the sequencer. And this is what we call like the amount of work, right? And this is denoted as like this big blue blocks, like the execute transaction. Takes for like the amount of work that takes to execute this transaction. And then we have the validator, which is on layer 1. And then this is the amount of work they have to put in to do the verification. And this amount of work is basically log square of X, which is polylogarithmic time. We can also plot this on a chart, and the blue line is basically sequencer's amount of work to perform. And then I think it's yellow or orange. The orange line is basically the amount of work done by the validator. And our goal is to make this gap even bigger. Like, how can we make this gap even bigger? And just to note, I think this is just the baseline. So there's no recursion on this chart whatsoever. So it's just the baseline. Now, as we talked about, the sequencer job is only to execute the transaction, but it doesn't generate the proof. So we never discussed like what's the amount of effort to generate these proofs overall, and how much resources like the sharp prover does. So this is back the question: how much amount of effort does the prover do? On the next slide, I think, if I click it, this is the amount of work that a prover does to generate the validity proof, right? And we can see that even on the chart, the yellow, the orange line is the amount of work that the prover does to generate the work, and it grows at a much faster pace than the amount of work done by the sequencer. And this is kind of like a bit problematic. Like it takes quite a lot to generate this amount of to generate the validity proof. So it introduced new challenges, such as you kind of like need a more powerful computer for the prover to actually keep up with the load from the sequencer. And having a more powerful computer means that you also increase the cost, or it becomes more expensive to have these machines. So the question is, can we actually narrow this gap significantly, or like can we narrow this gap and make it significantly cheaper and feasible? Also, just to notice, you can actually click like these plots have been done by David. Thank you, David, for these wonderful plots. And you can actually click on the Wolfram Alpha, and it will basically bring you to these plots. Okay, now let's analyze the problem in two different ways. We're going to analyze it by creating a proof in sequence with a single prover, and we're going to compare a small proof versus a bigger proof. So we have the smaller proof that we'll analyze first. And initially, let's say we have 3 transactions. These 3 transactions are being bundled into a block, and then the block like from the block we create a Cairo job. And you can imagine a Cairo job is basically transforming these individual transactions into a single Cairo program that does all of these 3 things as part of the execution. That's basically a Cairo job. So the Cairo job is being sent to the prover. And then here we can notice that the proof creation is, I actually forgot to say that this amount of work, so X log X, is actually quasi-linear time, right? So this is the amount of work that the prover has to do. And then the verification by the layer 1 or the verifier is basically polylogarithmic time. And the Cairo job is basically X, or in this case. Let's analyze a bigger proof. So we go into the other extreme. We create more transactions. We have more transactions that we bundle into a block, and then we create a single Cairo job out of it. As a reminder, Cairo job is basically transforms all of these individual transactions into a single Cairo program that does all of these things of execution. This Cairo job is being sent to the prover. And now we can see that the amount of work done by the prover, it's actually much, much more. And then the verification on layer one, it slightly increased. It's mainly because it's polylogarithmic time. And the proof, the generating of the validity proof, it's quasi-linear time, so x log x. Now, there's basically a trade-off between these two. So initially, the smaller Cairo jobs we have and more frequent the proofs, we're going to reach faster finality on layer one. But this means that the trade-off is we're going to have higher transaction costs, because the transaction costs it's going to be like spread out between these three transactions, which means it's going to be a higher transaction cost. Now, compared to the bigger proof, which is the other extreme, we have slower finality. So basically, we have like a bigger Cairo job, like bigger transactions, but we have less frequent proofs. So the trade-off is that because we have less frequent proofs, it means that we have a slower layer one finality. But then the other benefit of this is that we have lower transaction costs, and mainly because the cost is spread out between all of these transactions. But it's still like it requires quite a lot of time to generate these proofs. This begs the question: is there any alternative to it? And I would say yes. There's actually a hybrid approach that takes care of this so-called recursion, and we'll look at it in just. So initially, we talked about Sharp, the shared prover. We did a lot of simplifications in the previous slides and the last session, but Sharp prover is more than this. Like, it's more than one prover. It's more than Starknet. It's actually a very powerful machine to think about. So the Sharp prover basically has more prover modules attributed to it, and it also serves not only Starknet but other protocols. So we discussed about this, that Sharp means shared prover, and it's being shared with Starknet, with the DOIDX, with Sorare, with Herodotus, Rhinify, and so on and so forth, right? So it's a shared prover that it's being used by these protocols. And Sharp actually has, like, behind it, there's multiple provers running simultaneously. And basically, there are a lot of modules that allow us to do parallelization in proving and independently creating these validity proofs. And we'll see this in a second. So like, if somebody asks about like what's Sharp, it's basically a super, super powerful machine. That's what I would say. So let's analyze that, like the recursive proofs. So we'll try to create a proof in parallel with multiple provers, right? Like, we generate the proof with multiple provers. So initially here on the right, we have the legend. We have, I think this is teal or green maybe. It's proof generation done off chain. And then with yellow, we have the verification with Cairo, also done off chain. And finally, we have the verification with Solidity that's being done on chain. So initially, we have a prover that receives this job to create a proof for or validity proof for Starknet. But in addition, maybe, like, simultaneously, there's other provers that needs to be generated. So this is, for example, from DYDX, Sorare, and Rhinify. As I mentioned, these we are able to run these parallel and simultaneously, and to generate proofs from this independently. So what happens next? After the validity proof is being created, this validity proof is not sent to the layer one on Ethereum. It's actually sent to an internal module that's part of Sharp. And this internal module is actually a verifier written in Cairo, right? And because it's a Cairo program, you basically are able to prove, like, Cairo is a provable program. So you're able to create a proof out of it. So what happens here is that the proof, the validity proof from this is being sent to the internal module that verifies this. And then from here, what we can do is we can create a new recursive proof out of it, which basically attests the validity of these two. This happens for Starknet DYDX in this example. We create a recursive proof here. And then we do the same process for Sorare and Rhinify. We create a recursive proof that attests the validity of these two Cairo programs. Now, the same process repeats itself. These validity proofs from these two Cairo programs are being sent to the verifier, the internal module. And then from this, we're going to create a new recursive proof. So this is where the recursion happens, right? We bundle these two together. We have a Cairo program. We create a recursive proof of it, and we repeat the same process again. Only because the internal module, the verifier, it's a Cairo program that allows us to do this. And this is off-chain. And finally, we reach the R2, which is a level 2 recursion in this case. And this is the validity proof that's being sent to the layer 1 verification on chain. So sending the validity proof at the end will make it much cheaper, because verification on-chain is quite expensive compared to the off-chain verification. And the cost the cost is basically spread among these protocols. So in essence, this is just a simplification of the whole recursion. There's a deeper complexity to it, like a deeper level of recursion that's happening currently on Starknet. And David, correct me if I'm wrong. There are, I think, 128 modules that work in parallel or something like that.
Yeah, that's all right. We have some questions in the Q&A if you want to tackle them before continuing. I mean, I don't know if you finish this slide, but maybe finish the slide and you can take a look at the questions.
So I have a GPU farm in Paraguay where the electricity is cheap and 100 renewable. Can I eventually accelerate Starknet proofs? So that's a good question. I think that half a terabyte of memory is actually a prover or module that works. So I'm not sure if your machine is that powerful enough, but actually the prover modules are very powerful machine. But in essence, as part of the decentralization, once the decentralization robot is in place, it might be possible. But currently, since everything is centralized, it's not possible. Hopefully that answers the question.
You can, however, set up I mean, you can use Cairo outside of a Starknet if you want, and in that case, you need to prove it, right? So you can create a service just to prove Cairo computation for now outside of a Starknet. But as Robert mentioned, the biggest requirement will be memory more than anything else at the moment. But you can play around with the Stu prover if you want to see some of the requirements and how it looks like.
Exactly. And just to illustrate this, this is the stone prover. This is the prover that actually goes into production. And this is the one that works. And you can use this to actually generate the proofs by yourself. And then there's Stu prover. Stu, do I have Stu? I don't have Stu here. Let me see here. So Stu prover, it's a new next-gen prover that uses Circle Starks. And just to give you a TLDR, this is, I believe, 1,000 faster than the Stone 1 prover that we have, and it will tremendously scale the whole thing. So this is the next state of the art for proving systems. Okay. Is Sharp a cluster of machine where each machine is a prover, or a single machine multi-threaded? So that's a good question. If there's multiple of machines. Each machine it's in a half of terabyte memory, and they all act independently, and you can parallelize this. But are they multi-threaded? I'm not entirely sure. Maybe David, if you know.
No, I don't think they are. I think just independent machines. They just work together.
Got it. Why do you necessarily need the on-chain proof verification? Well, the on-chain proof verification, you need it at one point to settle on Ethereum, to actually settle the whole Starknet state on Ethereum. So at one point you have to do the on-chain verification. Now the question is, when you do it, it's important to do it. If you do it super early, then the cost of the verification is gonna be quite expensive, because we've seen this example here, right? So this example is it. So the faster that we reach L1 finality, the higher the cost. And then the slower we reach finality, the lower the cost. But now we try to improve this idea with proof recursion. We're going to see how this proof recursion helps us to have even faster finality and even lower cost, if that makes sense. Okay, I'll continue because we have still a few slides left, and then we have a 10 minutes session. So yeah, So basically, we reach like with this, like if you can imagine, with proof recursion, we reach a faster finality and a lower on layer one, because it takes less time to generate these proofs, and we can run these in parallel, and the transaction cost is much lower because it's spread among these protocols. So now let's see actually like how like the improving performance. How much does recursive proving improve the performance overall? And we have two main objectives here. We have the verification baseline and the proving baseline. And initially, the verification baseline here, we try to achieve how much wider the gap between these two is. So if you remember, this is like the amount of work done by the sequencer, and then this is the amount of work done by the validator on layer one. So this is like the polylogarithm. So now, as a sake of an example, here what's important is that we try to show the logic. So the numbers really don't like the mathematical numbers that you'll see here. It's not that relevant. It's important to understand the logic behind it and to, in the end, to visualize it on the plot to give a better perspective. So we'll try to explain the baseline. So here we have the caret job, which is denoted by X, the number of steps that it requires to execute that caret job. Then we have the prover, that is quasi-linear time, X log of X. And then we have the verifier on Ethereum, that's polylogarithmic time. So we plug in the mathematics, like the formula. So we have Ethereum, we're going to have log square of 4x. Again, don't really delve into too much about these functions, but this is just to illustrate the logic behind it. Now, let's analyze the same 4 caret jobs, but with one level of recursion. And this is where it gets interesting. So we have, again, Starknet, we have Sorare, dydx, and Rhinify, right? So because we have one level of recursion, we can run these in parallel. And what happens here that the prover one basically is 2x of log 2x, and the prover 2 is 2x of log 2x. This is the amount of work that's done by the prover. And we're able to do this because we're able to parallelize this process. And in the end, the verification, this is the internal module for the sharp, the caret verifier. And this will be polylogarithmic of polylogarithmic log square of 2x. That's going to be the amount of work done the caret verifier. Now, we bundled, we combine these two proofs, or these two executions from the caret verifier. We combine them together, and this will be represented as 2 log of 2, or log square 2x. Then we have the amount of work done the prover, which is this formula. And finally, we have the final verification on like Ethereum, on the validators that perform this amount of steps. Again, take it with a grain of salt. This is just to represent the visualization of these level of recursions. And finally, we're going to look at the same 4 caret jobs, but with 2 level of recursion, which means that we can run these 4 jobs in parallel. So we have like Starknet, Sorare, dydx, and Rhinify. We have each prover as quasi-linear time, so x log of x. And then from each of these, we're going to send it to the caret verifier. And then from here, we can actually create a new recursive proof that's depicted by V1 and V2, or V3, V4. Then we're going to do create a validity proof for these 2 caret programs, and for these two caret programs. And it's going to be represented by this amount of work done by the prover. And finally, we have the V5 and V6 that we create another recursive proof. So this is the second level of recursion that happens. And then this is the last thing that basically is done. It's represented by this amount of work by the prover. And this is being sent to the validator on Ethereum that's represented by this number. So finally, let's try to see this in like terms of plots and visualization. I know it might be a bit too much in terms of notation, but we have first no recursion. So that's, if you recall the result, that's log square of 4x. Then the first level of recursion that's denoted by this for result. And then the second level of recursion that's denoted by this result. So what does this look like on the chart? And it looks like something like this. You can notice that with no recursion, it's actually much more expensive to do verification on layer one, right? And with one level of recursion, we already achieved, like narrowed this gap even further. I mean, we made the gap bigger. So, and then with the second level of recursion, it's even cheaper. So you can notice like there's a trend actually happening with the more level of recursion, the cheaper verification cost will be. Obviously, there's actually a trade-off of how many level of recursions you can achieve, but it's important to know like how we are able to scale the whole thing. Now, I think we're trying to explain like how does this look like in terms of like worked saved by the machine. So let's analyze the same process again. So we have the 4 jobs with no recursion, right? You have the prover that does the amount of work, and then we have the validator on Ethereum. Now, with one level of recursion, what happens is that we can run these two in parallel. We have the Cairo program that the Cairo verifier that verifies these proof, and then we can use that execution to actually generate the new recursive proof and then send it to the validator on Ethereum. And you can notice that we already managed to decrease the finality, right? So this is the amount of time it takes to actually do 4 jobs with no recursion, and then this is the amount of time to do with 1 level of recursion. So we managed to reduce the finality, like the time overall. Now with 4 jobs and 2 level of recursion, you can notice the same process again. We can run these in parallel. Then we combine the execution. We are able to generate a new recursive proof out of it. And then finally, we have the second level of recursion that's happening here. We generate the validity proof that's being sent to the validator on Ethereum. And then you can notice we even further reduce this cap in time, like in reaching the finality of this. So with no recursion, you have quite an expensive machine that has to do the all work. But with more level of recursion, you can see that the amount of work done by these machines are actually much less. So this means that you're able to run even cheaper machines to actually create these validity proofs. So this also saves a lot of cost in machine specification. Now, we put this in a chart to kind of like see the time to reach layer 1 finality. So for the previous example that we have for 4 carat jobs with no recursion, 1 level of recursion, and 2 levels of recursion. You can see with no recursion, it takes a lot of time to reach finality. With 1 level of recursion, this is being narrowed down. On the second level of recursion, I think David tried to plot this, but Wolfram kind of argued that it's too complex to actually plot it.
Yeah,
is that correct?
Yeah, I couldn't. Yeah, that's what happened.
Got it. So it basically, like, you can imagine that this is even lower than the first level of recursion, and the finality is achieved way faster with the more level of recursion that you add, and it saves time in the proving time as well. So in essence, with recursive proofs, we win across all the board, right? We get cheaper verification costs. We are able to run cheaper machines to do the proving, but we also can reach faster finality with it. So to kind of like reach a summary of the recursive proofs, Sharp, the shared prover, serves multiple protocols, not only Starknet, but also DYDX, Sorare, and so on. Sharp has multiple provers, so we've seen this powerful machine that runs multiple provers that also allows the parallelization of them. And this basically allows us to do this combination of proof recursion that we have. We can combine using recursion, and more operations can fit on a single layer 1 proof. So remember that 10-hour proof that's being sent to Ethereum? So that proof is basically, you can imagine like this is like a recursive proof of multiple proofs that a lot of things happen. Like there's multiple operations happening. That's not only done on Starknet, it's also done by DYDX and other protocols. So there's quite a lot of things in that single proof. And in essence, all of this recursive proving, what it does, it reduces the layer 2 transaction cost. It reduces the time to reach the layer 1 finality and reduces the proof respect. So we'll be able to run cheaper machines. And I think that summarizes the whole session. So let me see if there's a question. How the allocation of proof is distributed among the protocols? That's a good question. I actually don't know. think people from the start were able to tell you, but David, if you know how the allocation works.
No, I don't know. I think it's just as long as each one of these apps is requesting, hey, there's a carry job for me to prove, shall we just accommodate in the train of recursive proof and just add it to the single proof? But I don't know exactly the details how this is decided.
And there's another question. So the more recursive proofs, the faster finality. In essence, yes, but I guess you will achieve a trade-off. Like you will reach at a point that adding more recursive proofs will not necessarily be cheaper. So there's like probably a maximum depth that you can reach that is feasible in that sense. I'm not entirely sure how much is that depth, but it's quite a lot. Is the recursive proving is used only by Starknet among other ZK? So that's a good question. Are any other ZK rollups using recursive proofs? Maybe do you know?
So this is a funny thing. Internally, they've started to implement Starks as well, so they can do recursion. I know a couple of them do for sure because that's a winning formula, right? For performance. But they do that just because they have to do it's complex. They actually you get the Solidity code, they turn it into some kind of Stark compatible code. They do recursion on that, and then when that is ready, they don't send the Stark proof to Ethereum. They then prove that with a snark, and they say the snark proof to Ethereum. So there's more layers of complexity. So at the end, you have a snark proof going to Ethereum instead of a Stark proof. But internally, they're using Stark, many of them.
There's a question from Charles if there's a video from Vitalik running Stew software. Actually, I think I had that's from Starknet CC. So maybe you can type Starknet CC in YouTube, and then you can check the latest talk from Vitalik. He was very excited about Stew and how fast it is, and he made actually a presentation out of it. Got it. So for all protocols or layer 2, there will be only single verifier smart contract. So for Starknet, we do have like a smart contract on ETH that's the verifier smart contract. And that's where like the proofs are being sent. And then the all like node operators, those thousands and thousand node operators are actually picking this Validia proof up and validating it. So Snark do not allow recursion. David, maybe that's a question for you.
I don't think they do. I don't think it's possible. That's why they're forced to use internally Starks for this.
Starks all the way. Okay, and the last question, is there a folding scheme based recursion equivalent in Starks? Folding scheme. I'm not entirely sure. Maybe if you can check the Starks white paper.
Is that like for like KZG? Sounds I'm not cryptographer, but it sounds something like from KCG, and in which case it works differently.
Yeah, probably I would recommend the Starks white paper. Oh, he's talking about Nova. I'm not entirely sure. Okay, I'll respond to the other questions in chat. Thank you everybody for joining and tuning in for session 2, the deep dive. Thank you to the TAs and David for helping out with the question. And thank you for participating. Wishing everybody a fantastic week, and until next time, take care.
Bye.